So hi, everyone. I know I'm the only thing keeping you from lunch, but this is going to be a fairly fast-paced technical session, so it's going to be fast. So as Jeffrey mentioned, my name is Sara Soueidan. I'm a freelance front-end developer. I am based in Lebanon, but I work with companies across the globe, although most of my clients have been, all of them have been based in the US and Europe so far. I do front-end development. I'm specializing in HTML, semantics, accessibility, responsive web design, modern CSS, and all that awesome stuff. And I also do training and workshops, both at events and in-house. And currently focusing on accessibility, so running workshops on accessibility. Now, when I run workshops in-house, I try to customize the contents of the workshop to match my clients' needs as much as possible. So usually, a few weeks before I run a workshop in-house, I contact the designers and the engineers that are responsible for setting the workshop up, and I ask them if they have any specific pain points that they want me to address in the workshop, or if there is anything particular that they would like to learn, so that if I don't already have that in the workshop, I can add it. Now, a little less than 2 years ago, I ran my SVG workshop for Netflix engineers, and just like with all of my previous workshops, I contacted one of the engineers before the workshop, and I asked him if there's anything specific he would love to learn about. He said that he was interested in learning about SVG filters. He knew that they were capable of something really good, very powerful on the web, but he wasn't really sure how to deal with them, because the syntax of SVG filters can at first seem very intimidating. So upon his request, I started digging a lot into SVG filters, and then I added a section about them in the workshop, and then most, if not all of the research that I did and everything that I've learned, I filtered down and turned it into this talk that I'm going to give today. So what I'm hoping is that by the end of the talk, I will give you a clear and hopefully inspiring idea of everything that SVG filters can do, or even though we'll only be scratching the surface of what's possible, and hopefully get you excited about the possibilities that SVG brings to the web as I am. So over the last few years, you probably know that the gap between what's possible to do in graphics editors such as Photoshop, Illustrator, and in print design in general, and what's possible on the web, the gap between these two has been getting smaller and smaller over the last few years. First, with the addition of features to CSS, such as CSS shapes. These are all demos that I created using CSS shapes, where you can wrap content inside and around non-rectangular shapes. And then the introduction of CSS blend modes, which enable us to do a lot of color compositing and blending to create some really interesting text and image effects. And then there's also CSS filters that enable us to do image editing right in the comfort of our code editors. Now, there are currently 11 filter functions in CSS that do a range of effects from blurring to changing color contrast, saturation, etc. One particularly interesting filter function is the URL function, the last one on the list, which provides us with the ability to import more complex filter effects, other than the ones available in CSS, from SVG. Now, it is true that CSS has made the gap between print and web smaller, but the truth is that that gap has always been smaller. It's just taken us an awful lot of time to realize or to pay attention to the parts of the web that do make it smaller. SVG, which has been around for more than 2 decades now, has always had the ability to create Photoshop-grade, and I'm not exaggerating, Photoshop-grade effects in the browser, all the way from the start. In fact, CSS filters are imported from SVG. The filters in CSS, the filter functions are shortcuts for a subset, just a small subset of filter primitives. We call them primitives instead of functions in SVG. So the CSS functions are shortcuts for a subset of filter primitives available in SVG. The CSS counterparts are fairly more optimized versions of the SVG filters that have been around for a very long time. And the SVG versions are capable of far more than their CSS counterparts. For example, it is currently possible to blur an object or an image or text, anything basically, using the CSS blur function. In the image here, we're blurring the image by an amount of 6 pixels, which creates a uniform blur effect that is equally distributed along the x and y axes. But this function is merely a simplified and limited shortcut for the blur filter primitive that is available in SVG, which allows us to blur an image either uniformly like we can do in CSS now, or apply a one-directional blur effect, horizontal or vertical. And then when you combine this blur effect with other filter effects in SVG, you can create more complex and more interesting effects such as motion blur, to just name one example. Now, also, SVG filter primitives are not limited to image color manipulation. So we're not just talking about image and then editing images like we do with CSS. They are capable of much more than that, as you're going to see in this talk. Now, the question that usually pops up when I have conversations about filter effects on the web is why? Why would you want to apply filter effects to content on the web when you can just go create something, create some effect in Photoshop, export that as an image, and then embed it? That's easy and fast using an image tag, right? Now, the answer is, first of all, in today's responsive web, we cannot talk about one image anymore. We need, usually, when we're exporting and embedding images, we need to create multiple versions of that image and then serve the appropriate image using source set or the picture element, depending on the user's current context, right? So we're not dealing with just one image, we're dealing with more than one image. And then any change that you want to apply to that effect that you have, you're going to have to jump back into Photoshop or Illustrator or whatever tool that you use, change that, re-export all of the images, and then re-embed them. That is not very ideal. But having an effect done in the browser means that your effects are resolution independent, so you no longer have to worry about 1x, 2x, 3x, etc. The effect is easier and faster to tweak and change. You don't need to jump into your images, your image editor, change, export, re-embed. The content is editable. You don't need to change, if you need to change the text, if you're applying an effect to a piece of text and you need to change the content of that text, you can do that in the browser, again, without having to jump into a graphics editor. And content semantics are preserved because when you're applying a graphical effect on the web using web technologies like CSS or SVG, you're applying that to real text, HTML text, or even SVG text. That text is searchable, selectable, and accessible, whereas text replaced by an image is not. And the effects are animatable. So my absolute favorite thing about SVG is that it is both a document format and an image format, and it's a very powerful document format. This means that just like with HTML, you can apply CSS and JavaScript animations to the content of an SVG, just like you can to the content of HTML. And because SVG filters, as you're going to see, are actual SVG elements, you can also animate those filters, therefore animating your effects, which is not possible with static images. Now, filters in SVG are created using the conveniently named filter element. Now, almost everything in SVG is conveniently named, so you can tell what the element is or does just from its name. Filter elements are never rendered directly. Their only usage is something that can be referenced using the filter property. So we have a filter element that would contain something inside of it, and then using the filter attribute on the image, we're applying that filter to that image. Usually, elements that are not rendered directly are defined inside of defs element in SVG. So a defs element is short for definitions, and everything you put inside of a defs element is not going to be rendered on the screen unless you specifically ask for it to be rendered. But SVG filters don't need to be wrapped inside of defs element because whether or not you wrap them, they're not going to be rendered. The reason for that is that a filter requires a source image to work on, and unless you explicitly define that source by calling the filter on that source, so you define an image and you call that SVG filter on that image, then the filter is not going to have anything to be applied to, and so it's not going to be rendered. Now, a filter effect is made up of a series of operations that are applied to a given source graphic to produce a modified graphical result. So in SVG, each filter element contains a set of filter primitives or functions as its children, all prefixed FE. So we have FE offset, FE Gaussian blur, FE flood, FE blend, FE composite, FE merge, and so many more. FE is short for filter effect. So each filter primitive performs a single fundamental graphical operation on one or more inputs, producing one graphical result. The input of a filter primitive can be either the original image, the original source graphic, we call it. So if you're applying an effect to an image, that image is the source graphic. If you're applying an effect to a piece of text, that text is the source graphic. The input can also be the alpha channel of that source graphic. We're going to see examples of why and how that can be very useful. Or the input of one function can also be the result of another function, another primitive. Now, since you can use the result of one operation as an input to one or more other operations, this means that there's an almost endless set of possible combinations, and therefore an endless set of possible filter effects that you can create using SVG on the web today. So this is code. You don't have to worry about all of it now. So these are just a few examples of some filter primitives. We have FE offset. It takes in a source, which in this case is source alpha, the alpha channel of whatever we're applying it to. There's also FE composite. Some filter primitives take 2 inputs, so it's usually because you're going to use one of them to affect the other. You don't have, so right now you have the in attribute, the in2 attribute, but there is no in3, in4, and 5. It's either 1 input or 2 inputs. Now, in order to ease into the world of SVG filters, I'm going to start with one of the very basic and simpler effects, which is creating a drop shadow. Because a drop shadow is very simple, but it also requires multiple steps and therefore multiple simple filter primitives in order to be created. It's usually a nice way to ease into the world of SVG filters. This is what we're aiming to create, a simple translucent black drop shadow offset behind an image. Now, I know if you were to create this in CSS, you could just use the drop shadow function, but it's going to take a few more steps in SVG, but there is a reason I'm doing this as an example, because, as I mentioned, just to ease into the SVG filter primitives and how to use them. So we're going to start by creating our filter container, which will house all of our filter operations, and then we will be applying this filter to the image that we have. Then we start by creating the drop shadow step by step. First, we start with the FE offset. The FE offset filter primitive is used to offset its input by a certain distance along the x and y axes. You have dx and dy. They determine the amount by which you want to offset your input. Now, since we want to create a blurred, translucent copy of the image, it makes sense to take the alpha channel of that image, which is just a black rectangle, and then make that translucent and put that behind the image, right? So the input for the offset, FE offset filter primitive is our source alpha, which, as I mentioned, is the alpha channel of the image. Since the image is fully opaque, then the source alpha of the image is just a black rectangle. Then we're using that input as input, the output of the offset as an input to the Gaussian blur filter primitive. Now, a quick thing to note here is that if you don't specify the input of the Gaussian blur, I'm not using the in attribute here, it is automatically going to use the result of the primitive that was right before it. So right now, the result of FE offset is being used by FE Gaussian blur. We're blurring it by 10 pixels, and we're giving the result a name, which is drop shadow. And this is the result that you would have rendered on the screen, a blurred black rectangle. Next, we need to make the shadow translucent. We can do that using the FE color matrix primitive. So color matrix is a filter type that uses a matrix to affect color values on a channel-by-channel basis. Think of it like editing channels in Photoshop. So you have a matrix with RGB channels, RGBA, and then you can edit each one of those channels in order to get a specific result. Una Kravitz has a fantastic article on Elistapart all about this matrix with examples and how to use it. That is definitely worth checking out. So we can choose to change one or more channel inside of our matrix. And since where's my mouse? Here is it. OK. Since we don't want to change any colors, I'm keeping the RGB channels equal to 1, which is the identity matrix. And I'm only changing the value of the alpha channel here. And I'm changing it from 1, which is the default, to 0.3, which basically makes the image translucent. So I'm taking in the result of the first 2 primitives, which is my black blurred rectangle. I'm using that as an input to my FE color matrix, and using that matrix, I'm changing the opacity of that rectangle to 0.3. Next, we need to make sure that, so I have a shadow now, and I need to make sure that I put my image on top of it, or layer my image on top of it. In order to do that, we use the FE merge filter primitive. As the name suggests, merge is used to merge effects or layers together. Each layer is specified in its own merge node element, and since we want to merge the source graphic, which is my image, and the result of these 2 other operations, or 3 operations, each one of them gets a merge node of its own. So the result of all of my previous operations was called final shadow. And I also have my source graphic, and I want to layer them on top of each other. So I have a merge node for the final shadow and a merge node for the source graphic, and I put them on top of each other. The merge node that comes last will be rendered on top of everything before it. So I have my blurred rectangle in the back and the image on top of it, and this is how you create a simple drop shadow in SVG. You can find a live demo of this code bin available in the talk slides, and you can play with it and tweak it and see how it changes. Now, to continue a little bit more easing into the world of SVG filters, I want to talk next about another very simple primitive, which is the FE morphology, which is used to morph elements. Now, to morph means to transform the form or the shape of an object. The morphology filter operates on the form of an object and provides two specific shape transformations: erosion, which is thinning or shrinking, and dilation, which is thickening or expanding. In more technical terms, this is a little bit technical, a little bit boring, but it's, I think if you know what's happening behind the scenes, it helps better understand it. Now, in more technical terms, both of these operations operate on a pixel level, expanding a pixel into its neighboring pixels, which is the dilate, or crumbling the neighboring pixels at the edges of the pixel being operated on. The amount by which a pixel is dilated or shrunk is specified inside of the radius attribute. Now, think of this radius as a radius of a circle or ellipse, and any neighboring pixels that lie within the circle determined by this radius, and starting at the input pixel, then counts, every pixel that lies in the circle counts as a neighboring pixel and will then be used to either shrink or expand to get the shrinking or expanding effect. Now, morphology applied to images, you can either apply effects to images or to text on the web, right? When you're applying FE morphology to an image, it has two very predictable results. The image dimensions get either smaller or larger, depending on whether you're eroding or dilating. On the top right, you can see that it's a little bit smaller, and on the bottom left, it's a little bit larger. And the image looks like it's been painted with a large painting brush with not a lot of details in it. So this is also visible here. In addition to the shrinking and expanding effect, probably the first thing that you may have noticed is that the different colors resulting from each one of these two effects. Erode produces an effect that has more darker pixels than the light ones, whereas dilate produces lighter output. This is due to the fact, this is a video showing how the dilation happens. This is being animated. This is due to the fact that erode sets each pixel to its darkest or most transparent neighbor, whereas dilate sets the channel of each pixel to match the brightest or least transparent value. Now, this is in case of an image. An image has different colors, and then the way the colors change depends on the image. For single color objects, such as text, which are usually monochrome, unless you're using one of the awesome variable fonts and new typography stuff. We're talking about basic text here, which is usually one color. The erode makes the object thinner, and dilate makes it thicker. But how is that useful? We can take advantage of this fact in order to create external outlines to text that give us more desirable results than what we would normally get using the more traditional SVG outline. So if you have a piece of text inside of SVG, or even HTML for that matter, and you want to apply an outline to that text, this is what the text looks like when it is outlined using an SVG stroke in the middle, and then when it's outlined using the SVG morphology filter. When applying an outline using the stroke attribute, you're applying that outline at the expense of the text itself getting thinner. It's practically that you're taking a part of that thickness of the text and then using it as an outline, which gives us undesirable results because we want to add an outline, but we don't want our text to become thinner. So in order to preserve the thickness of the text and add an outline to it, you can do that using the FE morphology. The code is a little bit more verbose, but the result is worth it. So using a stroke is as quick as adding the stroke attribute and the stroke width to that element that you want to be outlined, and it's pretty quick and straightforward. But again, this result is not desirable. To create the outline using SVG filters, you can do something like this. So I take my source alpha. In this case, I'm taking the alpha channel of my text, which is a black copy of the text. I use FE morphology to dilate that text. So I'm expanding the piece of text so that we get the result here. Okay. Next up, I want to colorize that outline. So I want the color of the outline to be different from the color of the text itself. In order to do that, you can Usually, generally speaking, most of the times, if you want to apply a color to something inside of SVG filters, you will use the filter primitive called FE flood. FE flood, as the name suggests, is going to flood the filter region, the filter area, where you're applying the effect with color. So in this case, I have FE flood. I'm applying a deep pink color. I'm giving it opacity. You can change that. I have it set to 1. And the result of this operation, which is a flood of color, I'm calling pink. Okay? So when you apply FE flood to a filter effect, to a filter region, everything in that region is going to be covered with a pink color. Everything. And that's why it's called flood, because it floods it. Now, in order to remove that extra flood area, you use the FE composite, which is going to composite that pink color with a piece of text. Compositing is the combining of a graphic element with its backdrop. A backdrop is the content behind the element and is what the element is composited with. So compositing defines how what you want to draw will be blended with what is already drawn on the canvas. The source is what you want to draw, and the destination is what is already drawn on the backdrop. So if we were to go back to our example here, I have a flood, which is the topmost layer, which is all color, and then I have the dilated text behind it, and I want to composite these two together. Now, there are different types of compositing effects, and depending on what compositing you use, the result changes. So in our case, the dilated text is the destination, and the flood color on top is the source. And compositing these two using the in operator will only render the area where these two intersect, which happens to be the text itself. And the area will be colored by the flood color because compositing blends things together. Am I making sense? Okay. So in other words, compositing the flood color with the dilated text is how you colorize that text. And at this point, the colored shadow is the only thing that is rendered on the screen, so we need to make sure that the source graphic is, again, layered on top of it, and that can be done, again, using the FE merge filter primitive. So I take the recolored back or dilated version of the text. So the pink text is the dilated version of the original text, and then I put the source graphic on top of it, and this is how you add an outline to a piece of text. You can also do something more interesting than that, which is create knockout text. So you have a piece of text, and you see through that text, and you see everything that's behind it. The code to achieve this is much shorter than the previous example, and there is a reason for that. So in order to create that knockout effect, I only use these two steps. The first one, I'm using FE morphology to dilate the text because I'm creating an outline. But if you can spot the difference here, what's different here is that the So I have FE morphology, and the input that I'm taking for FE morphology is the source graphic itself, or the text itself. I'm not taking a black copy of the text and then colorizing it. I'm taking the text itself and dilating it. And then if I want to change the color of the outline, all I have to do is change the color of the text itself, and since the text is being used to create the outline, you can customize the color of the outline using your CSS. That's separation of concerns. Whereas if you use FE flood, whenever you want to change the color of the outline, you have to jump into the SVG filter and change the value of the FE flood primitive. So I'm using FE morphology. I'm taking my text, expanding it, and then compositing it. Then I'm using, in the second step, I'm using the original text to composite on top of the dilated text to cut out the part of the dilated text where it overlaps with the text. Does that make sense? Okay. Next up, I want to talk about some more interesting things. So the first two examples were a way to hopefully ease you into the world of SVG filters and make them a little bit friendlier to read. This is where the interesting stuff starts. Now, I want to talk about how you can use an image of a texture and use it to change the shape or texture of other elements. In particular, I want to create this effect that I borrowed from a Photoshop tutorial that I found on YouTube. In the video, I'm not a designer, so whenever I want to create something, I look for a design video, see how the designer creates that, and then I try to recreate that using code. Now, in the video, the designer created this effect by using what is known as a displacement map. A displacement map is an image whose color information is used to distort the content of another element. So let's see exactly how that's done. In Photoshop, the steps to create that effect are as follows. So the designer has an image. He starts by applying a black and white effect. Oh, he also blurred it, by the way, at first. You blur it, you make it black and white, and then you export that as a graphic, as a displacement map, sorry. And then you add it again as a background, you add the piece of text, and then you use that image that you exported before, the black and white blurred version, you use that to displace the piece of text by a specific amount, a specific scale that you can tweak. This is my displacement map. Applying that to the text, you displace the text in 3D so that it looks that it's part of the texture behind it. So to recap, in order to create and use a displacement map in Photoshop, what you do is you desaturate the image that you want to use as a displacement map. You reduce the amount of detail in it by blurring it by 1 pixel, sometimes less, sometimes more. The reason we blur the image is that the more detail you have in the displacement map, and then you apply that to a piece of text, the less realistic the result is going to be. If you have too much detail, it's not going to be very realistic. If you have too little detail, it's also not realistic. So usually, blurring the image by an amount of 0.5 to 2 pixels maximum is more than enough to get you that level of details that you need. You save it as a displacement map. This is, again, the Photoshop steps. You create the text, apply a distortion filter using the image as a displacement map, reuse the original image as a background behind the text. These steps are actually so you reuse the image and then you apply the distortion filter. And then you can refine the effect a little bit more by adding slight transparency to the text, using blend modes to blend the color of the text with the background, and you get a more realistic effect. So how do we do that in SVG? To create and use a displacement map in SVG, we use the FE displacement map primitive, again, very conveniently named. In SVG, the FE displacement map primitive uses the pixel values from the image in into to spatially displace the image from in. So we have in, into, two inputs. Into is used to displace in. If we were to recreate the Photoshop effect in SVG, the steps would look almost exactly identical to those that we had in Firefox and Photoshop. We start by filling the filter region area with the image that will be used as a texture. So in SVG, we have an image element, and using that image element, you can put an image inside of your SVG. But since we're dealing with an SVG filter, inside of an SVG filter, we can't use image, so we have an equivalent, which is FE image. When you use FE image, you are literally getting an image and then putting it inside of that filter area. You desaturate the image using FE color matrix that I mentioned before, the one that changes the RGB channels. It comes with a few shortcuts, convenient shortcuts. So if you set the value of color matrix to saturate, it allows you to apply a black and white effect to the image. You'll see the code shortly. You apply a 1 pixel Gaussian blur to the image using FE Gaussian blur. You use the image that you've just created to distort the text with FE displacement map. You blend the text into the background image using FE blend, and then apply a translucent effect to it. Decrease the opacity using another filter primitive called component transfer. I love that primitive. And then you display the text and the image behind it by merging the two layers using FE merge. So let's start by doing that. I have a filter. I'm starting with FE image. I'm referencing that image that I want to use as a displacement map. And then I'm desaturating that image so that the result of FE image is going to be used as an input to color matrix. Color matrix has a type attribute. It can either be matrix, which means that you provide a matrix and then change the values in that matrix any way you want. Or it can also come with shortcuts, and one of those is called saturate. So if you set the type to saturate, the values is between, I think it's between 0 and 1. So so FE color matrix value saturate. If I set the value to 0, which means that I'm completely desaturating the image and therefore making it black and white. And the result of this operation, which is a black and white image, I'm calling image. And then I decrease the level of the details of that image by using FE Gaussian blur, which is the last line here. I'm taking the image as an input, standard deviation 0.5. For this particular effect, I found that blurring it by 0.5 pixels was more than enough. And I'm calling the result map. And this is what I have right now. And then using FE displacement map, that map is my into input, which is going to be used to distort in, which is my source graphic. So I'm taking my source graphic, taking my displacement map, and then using the map to distort my text. The scale, X channel selector, and Y channel selector determine the amount or how strong the effect is going to be. So the higher the scale, the more intense the effect is going to be. And then I'm using the FE color matrix in order to apply a slight transparency to my text. And at this point, this is what my SVG is displaying. It's not displaying the image anymore because that image has been used to distort this piece of text. So this is what I have at the moment. Now, before I apply that image as a background to this text again, there's a little bit of enhancement that I want to make because the contrast in that image, I didn't really like it much. So in order to increase the contrast of my image that I'm going to use as a background, I get that image one more time. The first instance of FE image was used as a displacement map. Now I get that image one more time, and then I use the FE component transfer. Just like FE color matrix, component transfer allows you to do on a channel by channel, channel per channel editing of your images. So you have Func R, Func G, Func B, and then there's also Func A, each one of those channels. And then it allows you to apply a specific transfer function to each channel. In this case, I'm using the gamma function, which can be used to control the intensity and the contrast of the colors. Increasing the amplitude value increases the intensity of the colors. White becomes whiter, and darker shades become lighter. And the exponent value affects the dark areas of the image. Increasing the exponent intensifies the dark areas, and decreasing it lightens the dark areas, so you end up with a more washed-like effect. This is where the effect of the contrast is more obvious. So you increase the dark areas and decrease the light areas. And this is my image with a little bit more contrast applied to it. And then next, I'm blending the text with the background image using the multiply blend mode. And then I'm layering the original text with the background, not the original text, the distorted text with the background using FE merge. And this is the result that I have. Almost identical to Photoshop, except that I couldn't find that font face that he was using in the video, so I used a different one. So SVG can level up to Photoshop's capabilities in other effects too. Another example, in this section, I want to talk about how we can use FE component transfer, again, my favorite function, to manipulate the different color components of our images. Now, component transfer provides a few different types of component transfer functions. We saw gamma, which is used to control the contrast and intensity of colors, but it also provides different functions that enable you to create a variety of effects, from simple color manipulation and contrast changes to poster effects, for example, like this. So my original image is the one on the left, and if you want to give it a poster effect is basically reducing the number of colors in an image, and that's how you get a poster effect. Now, how can you do that using FE component transfer? So one of the other functions that FE component transfer provides is the discrete function. Discrete is used to reduce the number of colors in an image, and it shows more sudden color changes, which look more like the image was made up of bands or clusters of color. For every color shade, so different shades of red, for every one of those, you're mapping the colors to an X number of ranges, depending on how many X values you provide in table values. So for example, since we have 3 values in the table values attribute here of this snippet, the browser, this is my handwriting on an iPad, so don't judge me. I write much better on paper. The browser is going to divide. We provided 3 values and table values, right? What the browser will do is going to divide the red component into 3 equal ranges, 0 to 0.33, 0.33 to 0.66, and 0.66 to 1. Then any intensity of red for every pixel on the image, any intensity of red that lies between 0 and 0.33 in each pixel of the source graphic will be replaced with the red intensity 0. Any intensity of red between 0.3 and 0.66 will be replaced with 0.5, and so on. So a range of colors, range of intensities will end up being replaced with only 1, or 2, or 3. For an image that has a full range of red intensities like this one, the effect becomes very clear, and the workings of FE component transfer are more visible. Now, Again, this is just a way to ease you into what FE component transfer can do. So we saw gamma. Gamma allows you to control contrast and color intensity. Discrete allows you to create poster effects by decreasing the number of colors, mapping the colors that you have to a specific set of colors. And then it also allows you to do a lot more. So we can recreate duotone image effects exactly like the ones that you have in Photoshop using SVG FE component transfer. To create a duotone effect in Photoshop, again, I stole this from a video on YouTube, usually go through 2 steps. You turn the image into grayscale, and then you map the grayscale range into a new range that, instead of having black and white on either end, it has 2 different colors that you want to use as a duotone effect. In other words, you will need to use a gradient map that the browser will use to map your grayscale image to. So you start with a gradient of black to white, and it's being replaced with this gradient, in this case, from navy to some shade of green. In SVG, to create a gradient map, we can use the FE component transfer again, but in order to map the colors into a new range of colors, not a discrete number of colors, you want to map your colors into a new range of colors, you need to use a different FE component transfer function, which is called table. So, suppose that you want to create a duotone effect using these 2 colors here. Each color has RGB channel values. These values, for every one of those colors, RGB, the values of RGB are usually going to be in the range 0 to 255. And the values in the table values attribute are fractions between 0 and 1. So, to fill the values of the RGB channels inside of your SVG filter, we need to get the RGB values for our 2 colors and divide them by 255. Then, just like in Photoshop, the duotone effect can be created using exactly 2 steps. The first one is we're using FE color matrix to make our image grayscale. So when you have FE color matrix, and if you provide equal quantities of RGB, you essentially end up with a grayscale effect. The alpha is left untouched because we don't want to change anything about it. So we're making our image grayscale using FE color matrix. And then, using that grayscale image, I'm mapping it to the gradient that I created using these 2 colors that look like these. Now, FE component transfer will start to do its thing. The browser will go over each and every pixel in the source image. For every pixel, it will get the value of the R, G, and B components. Since our image is grayscale, the RGB values will be in the range 0, black, and 1, white. So RGB 0, 1. Then the value of each component will be mapped to the new range we provided in the table values. So the red component value will be mapped to the range 0.99 to 0.98. Blue is going to be mapped to 0.12 something to 0.941, and the RGB and the B is going to be mapped to 0.55 to 0.47. So by the time the browser goes over all of the pixels in the image, you will have replaced all RGB values in the grayscale gradient with the RGB values in the duotone gradient map. And as a result, the image becomes duotone. This is what my image looks like now. This looks OK, but there's something just not right about it. It could use a little bit of tweaking. In particular, it would be nicer if we made the highlights shine a little bit more, because his face looks very pale. We can do that using which color and using which primitive? Come on. Component transfer, yeah. So again, using the type gamma, which is used to control the contrast and intensity, I'm increasing the component makes the darker areas darker, and increasing the amplitude makes the lighter areas shine more. And this, in turn, increases the overall contrast of the image. And we end up with this, which looks much better than we had before. Now, in addition to applying texture to elements, SVG filters can also generate rich textures using noise. Textures that can then be applied to other elements and can also be animated to achieve effects such as these. Yep, that's SVG filters in action, or animated SVG filters applied to HTML elements. Now, this can be done using the FE turbulence primitive. FE turbulence generates and renders Perlin noise in your browser using SVG. This kind of noise is useful in simulating several natural phenomena like clouds, fire, smoke, and in generating complex texture like marble or granite. If you Google the internet a little bit, you will find examples of these textures created using SVG filters. Just like FE flood, FE turbulence fills a rectangle with new content, random noise. Now, in this section, I'm going to go over how we can create noise using FE turbulence, and how that noise can first be used to distort images, much like we did with the displacement map before. And then we're going to see how the generated noise can then be combined with SVG lighting effects, because yes, we have lighting effects in SVG, in order to create a simple rough paper texture. So the turbulence filter syntax looks like this. It comes with 5 main attributes that affect the generated texture. And most of the times, there are only 3 attributes that you need to worry about: the type, the base frequency, and the num octaves. Num octaves is short for number of octaves. Base frequency specifies the grain of the noise. Very low values, which are 0.00, such as 0.001, will produce large patterns. So a low base frequency produces large patterns, and very high values, such as 0.5, will produce tiny patterns. Values in the range 0.02 and 0.2 are useful starting points for most textures. There are 2 types of noise: turbulence, which is the default noise, which you're going to see shortly, and then there's also fractal noise. I'm going to have to say fractal noise quite a few times today, and I'm definitely going to be tongue-twisting, so if I say it wrong, please just remember fractal noise. So turbulence is the default noise, more grainy, and fractal noise has more cloudy and smooth pattern. The number of octaves, as I mentioned, is short for number of octaves, which presents the level of detail in the noise. The higher the number of octaves, the more detail that you can see in the noise. These 12 images represent 12 different results of noise created with FE turbulence, with different types, base frequency, and number of octave values. So in A, we start with a base frequency of 0.04. In B, we increase the detail level with a number of octaves set to 2. Same as C, but we change the seed. We're not going to talk about seed now. D is the same as C, but with a number of octaves set to 5, so D is C, but with higher detail. F is decreasing the base frequency to 0.01, which will create larger patterns. If you notice, if you look at, I think it's A and F. So when you're increasing the pattern, when you decrease the base frequency and you increase the pattern, it's literally like you have a big image of texture, of noise, and then you're zooming into parts of that noise. And that's what's happening with F. So when we decrease the base frequency to 0.01, we're zooming into the corner of that image, of that noise. G and H show the difference in number of octaves and the detail levels. H has more details than G. I and J show fractal noise, so the first images are all turbulence. I and J are fractal, which is more cloudy, more smooth. J is 3 levels more detailed than I. K and L show you that you can change the size of the pattern along the X or Y axes. The examples that I showed earlier with the button, let me try to go back to them. Yeah, okay. That is horizontal noise. The Perlin noise I just saw with the horizontal lines, that is that noise applied to the buttons. Okay. So there is a web app that, when I was learning about SVG filters, I looked for everything possible that could help me understand them. And there's this hands-on filter web app that allows you to create a noise, a piece of noise, using FE turbulence, and then apply that and see the result of applying that to an image. What's happening here is, if you look at the code here, we have the FE turbulence, and then it's being used as an FE displacement map to displace the image. So we're generating noise, and then we're using it to displace the image. You can also use it to displace text, which creates this kind of effect. Turbulence can also be used to create effects like these, splash, water splash effect. This is a demo from an article by Dirk Weber on Smashing Magazine. He has a ton of amazing text effects created using SVG filters. He has multiple levels of turbulence, in this case, generated and applied to different pieces of text, so you get this effect here. Turbulence can also be animated. So you can define multiple FE turbulence operations, like I have here. Each one has a different name inside of the filter. And then you can switch between them to get something like this squiggly text. So we distorted the text using FE turbulence, and then I animated into another turbulence and another one, and you get this squiggly text. This is by Lucas Beber, one of the most brilliant web developers that I've seen in my life. All the demos that he creates are fantastic, and they're going to burn your laptop down because they are very resource consuming. Now, animating turbulence can produce even more interesting effects like we saw with the buttons before. Again, I like this video. By the way, these demos are from CodeDrops. So next up, I want to talk about how you can use the generated noise from FE turbulence with the lighting effects inside of SVG to create a texture that you can also then use to distort text or do anything that you want with it. One fairly simple texture created using turbulence and lighting is the rough paper texture. This texture requires literally 2 steps and 2 filter primitives to create. So we're going to start by creating the base for our whole effect, which is the turbulence primitive. I'm starting with my filter. I'm calling it rough paper. I have an FE turbulence. I'm setting the base frequency to 0.04 and the result to noise. So I'm not setting any number of octaves. I'm not setting the type of the noise. I'm just telling it that base frequency is 0.04. I need somewhere to start. Right? And the only required attribute for FE turbulence is base frequency. So let me start with that. This is what I end up with. This is my filter region filled with random Perlin noise. Next, we need to shine a light on that surface. Shining a light on a graphic provides additional depth and texture. Okay? So to create a lighting effect, you need to specify 3 things. A light color, specified using a lighting color property, and a light type, specified using the types of light available in SVG. We have diffuse lighting, which indicates indirect light from an outside source, such as sunlight, or you have specular lighting, which specifies secondary light that bounces from reflective surfaces. Both of these primitives shine light on an object or image by using the alpha channel of that image as a bump map. So, to rephrase, a light source filter uses an input's alpha channel to provide depth information. The higher opacity areas are raised towards the viewer, and lower opacity areas recede away from the viewer. In other words, the alpha value of a pixel in the input is used as the height of that pixel in the Z dimension, and the filter uses that height to calculate a virtual space, a virtual surface, which will reflect a particular amount of light from your light source. Because FE turbulence generates an alpha channel full of noisy values between 0 and 1, it's random noise, so random values of R, random values of G and B and alpha. It produces a nice variable Z terrain that creates highlights when we shine our light on it. Now, after deciding on the type of light that you need, you'll want to choose a light source. There are 3 different kinds of light sources in SVG. A distant light, which is arbitrarily far away, and it's the most appropriate way to present sunlight. A point light, which emanates from a specific point, such as room lighting. And a spotlight, which behaves much like the second one, but its beam can be narrowed to a cone, and the light can pivot to other targets. To create a light source, we nest the light source inside of the light type, and then we finally specify the lighting color. To light the noise we generated earlier, we will apply a white diffuse lighting emanating from a distant light source. So I have my noise, and I have a lighting effect applied to it. The surface scale value in the diffuse lighting is the Z-index multiplier. Increasing this will create steeper virtual slopes in your texture. So applying this lighting effect to the turbulence that we generated earlier gives us this. Now, I can see that the first thing, I want to turn this into a rough paper texture. So the first thing that I notice is that we have too many sharp edges. So we need to smooth the noise out. How can we do that? What's that? No. What's that? Fractal noise, exactly. So there are 2 types of noise, and we mentioned that fractal is the more cloudy, smooth one. Okay, so I start by adding the type of noise. Instead of the default turbulence, I give it the value fractal noise, which makes it a lot more smoother, as you can see here. Now, this looks better, but when we're talking about rough paper, you know that it's rough because it has more smaller details. How can we increase the number of details or the amount of details in our texture? Num octaves, exactly. So 5 octaves is usually the highest that you'll need. The effect of a 6th octave is usually not very noticeable. So let's apply 5 octaves to this texture and see how it looks then. It should be all we need for this effect. Yep, this looks much better. Now we can change the effect a little bit more, tweak it more by playing with the light source, change the direction, take it up and down, etc., and the distance of the light. For example, decreasing the elevation of the light source, getting it closer, should increase the contrast between the small hilly areas, and the image would then look more like this, which brings us a tad closer to sandpaper, which is not what we want. So the previous one was more like what we were aiming for. And that's all that you need to create a simple texture in SVG: texture, random noise, and lighting effects. Now, you can get a lot more creative if you want to create clouds. Those clouds, if you want to create sky and clouds, you're going to need more colors, and then you would need to use FE component transfer and FE color matrix in order to change or tweak the RGB channels in your noise. And you can get very creative, and you can end up with, these are just base noises that you can use to create more complex effects. So we have something close to bokeh effects. I see some fireworks in the ones in the second row, but I don't know. So these are very good starting points and the results of applying different filter primitives to the noise that we generated. Now, before I end this talk, there is one very important concept that might trip you off if you're working with SVG filters and if you're not aware with it, and that is the concept of an SVG filter region. The set of filter operations that you have need a region to be applied to. Like when you have multiple elements in an SVG and you apply that, you have a filter and you want to apply that to only a specific area on that SVG. How do you define that area? Now, each element inside of an SVG has a small region whose boundaries are defined by the borders of the bounding box. The bounding box in SVG is very similar to the concept of a box in CSS. So in CSS, every HTML element has a width and a height, and every HTML element is a rectangle. So every HTML element has a box model on it, a rectangle with a coordinate system with the top left corner being the origin of that coordinate system. In SVG, we don't have that. There is no box model. Not all elements are rectangle. And so if you want to apply an effect to just one element, you need something similar to a box model, which in SVG is called the bounding box. The bounding box is the smallest fitting rectangle around an element. So for example, if you have a piece of text, the smallest fitting rectangle would look like the pink rectangle that I have here. Although more realistically, usually the bounding box also includes any line height. So if the line height of that text is higher, it's going to include some padding inside. Now, the default filter region of an element is the element's bounding box. Okay, so if you apply any filter effect to this piece of text, the effect is going to be restricted to this rectangle. And any filter result that lies beyond the boundaries of it is going to be clipped off. It makes sense because you have a region and you want to apply the filter to that region only. But sometimes when that happens, you get a very undesirable result because many filters will impact pixels outside of the bounding rectangle. An example of this is the blur effect. This is what happens when the text is blurred. You can see that the blurring is cut off on both the right and the left side of the text. This is not desirable. And according to the specification, it's often necessary to provide padding space inside of the filter region because the filter effect can impact pixels outside of the bounding box. And it's possible to provide negative percentage values for x, y, and width, and values greater than 100 for width and height. So the filter element that houses all of our filter primitives has x, y, width, and height attributes that define the area of the filter region. You can provide negative values and values greater than 100% in order to expand it. Now, this is also why the default values for the x, y, width, and height attributes on the filter, according to the specification, are -10%, -10%, 120 by 120. So you're essentially increasing the area of the filter region by 10% of that area in each direction. One thing that has helped me when working with filter regions is to be able to visualize that filter region area. The way I do that is I usually flood that filter region with FE flood. FE flood is going to apply a color to the entire filter region. And if I need to see my filter region, I usually flood it with a piece of some color. And again, because I want to move my text on top of it, I use FE merge and then put it on top. So whenever I'm dealing with something and I'm not sure where the region is, I like to visualize it like that. You can override the default filter region area by using the X, Y, width, height attributes, but you need to keep in mind that the filter units attribute, these are very small details, very technical, but if you're ever going to work with SVG filters or even clip paths or anything like that, you also have clip path units, for example. Clip path units determines what coordinate system is going to be used for the X, Y, width, and height. By default, the coordinate system is the bounding box of the elements, so you set it in percentages. 5% is 5% of the bounding box. But you can also change that to user space on use, which is the coordinate system of the entire SVG. And in that case, instead of using percentages, you need to use pixels in order to expand that filter region. Just a few things to keep in mind, because in SVG you have two coordinate systems, and then you also have the bounding box of an element. And depending on which one of these you're using for your units, it can get a little bit tricky. So just something to keep in mind. If you ever have a filter effect being cut off, try to visualize the region, change it, make it bigger or smaller, any way you need. You can also play with this in this code pen. And I have a bunch of filter effects that I created when I was learning about SVG filters. All of the demos in this talk, plus many more, are available in my CodePen collection. And that's it for me. Thank you very much.